All right. Welcome to Rich Conversations. We have another fabulous episode. I'm here actually recording, not in our typical setup, but my friend's apartment, Justina. She's been on the podcast before. So we have some lovely plants in the background. We have train tracks outside the apartment, so we might hear a little bit of noise. And we also have two lovely cats that come around. But we are joined all the way from Munich, Germany, by Matthias, Matze,
Matze.
Matze. Something I gotta get better on the pod is pronunciation. Welcome to the show.
I'm glad I'm here.
Yeah. Why don't you?
Nice to meet you.
Yes, you as well. Why don't you briefly introduce yourself for listeners and viewers?
Okay, I'm Matze. So the full name would be Matthias, but everybody just calls me Matze. I'm from Munich, as already mentioned, and I'm studying physics at the Technical University of Munich. And in my free time, when I have any, I like to spend time with friends, if I can, due to COVID, and make music, sports. But I have an injury, so can't do so much right now. And also, I discovered computer science for me now. So yes, and learning languages a little bit.
Wow. So yeah, you're a busy guy. How long have you lived in Munich for?
My whole life, and now I'm not living directly in the city. Okay. So when I was 2, my parents moved outside of the city because I have an older sister and a younger brother, and the flat got too little. So now we're living in a house.
Got it.
Outside.
What would you say, like, the general vibe is of Munich?
I would say it's you can say there's one general. It's but I think that's for most of the cities. But there's kind of the cliche of that the Munich people in Germany, that the Munich people are snobby, and and a lot of the rich kids. They are also superstitious, but I think that's true for some people, but not for most of the people that I had an experience with. Okay. So you got kind of two worlds and everything in between. But I think the people who are originally from outside of the city and also in the city, because there are also a lot of people who came from other parts of Germany, they value nature a lot. So we have a beautiful river in the city, and when even if it's cold outside in the winter, if the sun comes out, all the people are there, and we have a huge garden, a park, which is called the Englischer Garten. Okay. So this would be translated to English garden, and it starts a little bit outside the city center, but in the city, and goes, I think, about 20 kilometers out of the city. So I think that would be about 13, 14 miles. Okay. And alongside the river. So most of the people are connected to the nature, I think, and also spending time outside of the city, like doing sports or something.
Would you say it's how would you describe it compared to other cities in Germany?
Okay, I have to admit I haven't been to so many cities in Germany. I've been to, I don't know how exactly you would pronounce it in English, Cologne, I think.
Oh, okay, yeah.
Because Cologne, because my mother is from there.
Okay.
And I think the first thing that I would think about is that you have the how to say this in English, the Bavarian chillness, kind of.
Okay.
So you have a lot of subcultures in Germany, and if I think about Cologne, I think about Carnival, because that's a huge thing there. And here in Munich, we have like the Bavarian traditions the clothing and the Gelassenheit, it is called, and they have this in other cities too, like in Berlin, where I was also. But it's every city has kind of its own taste of this chillness and company with other people.
Yeah.
So that's very specific to the cities, I think.
So is Munich more like you're saying nature before? Is it people in like Bavaria, or a little bit more?
Yeah, I think Bavaria and also the other state. I don't know what the English name is. Baden-Württemberg. It's right next to Bavaria, and they're both two of the biggest states in the south. So both on the Alps, and so huge mountains, a lot of lakes.
It sounds relaxing.
Yes, it is. A lot of forests, also. By the way, a lot of fields, also.
Okay.
And where I live, there are also a lot of small fests in the spring. So, do you know the Oktoberfest?
Yeah, I think most Americans are familiar with Oktoberfest.
Yes, it's like a small Oktoberfest in more or less every little village.
Okay.
So every weekend you have in the spring some of them anywhere. And then you can go from one to the other.
What would you say, like if someone were visiting for a week or so, a few days to a week, what would you recommend them doing?
I would split this into 3 parts. So in the city, in the greater city area, and in the region. So in the city, I would, as I already said, visit of course the river, the English Garden, then a rooftop bar.
Okay.
There are a few. One of them actually at my university. We have a great view over the city. Then, of course, a traditional Bavarian restaurant, which is called a Wirtshaus.
Okay.
That's one of the greatest. Maybe is the Hofbräuhaus, Münchner Hofbräuhaus, which is really really famous. And then you can go from the Isartor, it is called. So you had an old city wall, and you have a few old doors through the city halls, and you can go from one to the other straight to the through the old city. Wow. There's also a huge market, and then you kind of see most of the things in the city.
What did you mean by like old city? You mean like what do you mean by that?
Yeah, it's not the one of the oldest cities in Germany. So I think Cologne is way older, but it was I think founded in 1200s or 12 to 1500s. Okay. And you have a few buildings over a few hundred years old, and that's the old city center. And you can go, as I said, from one tent to the other.
Wow, cool.
Then, if you have a little bit more time and can go farther, I would recommend to go to one of the lakes near the city. So a few of them you can actually visit with the public transportation, and that's kind of more like regional transportation. But you can also go to the mountains, or if in the winter you also see in the city people with skis and snowboards in the trains because they're going snowboarding and skiing. If it's summer, then going hiking. And if you have more time, then you can visit some of the other cities nearby. So also Austria is pretty near. So I would recommend visiting Austria for the mountains or for the cities. And yeah, I think that's about it.
Nice. Yeah, Germany is a place I definitely want to visit. Taking some notes.
Have you ever been?
I haven't been. I haven't been yet.
If you're here, then text me or write me an email.
Yeah, for sure.
I can show you around.
Yeah, Germany is definitely a place to go. Is the public transportation really good?
Yeah. You get where you want to be, but it often takes a lot longer than you think it would take.
Okay.
So especially if you do public transportation over longer distance, then in the summer there was a huge chaos, and you sometimes have to wait 5 hours for the train to start.
Really?
Yes. It was because of the don't know the vocabulary, the climate machines inside of the trains. How do you say it?
Like
air conditioning.
Oh, okay.
And the trains didn't work.
Okay.
And it was above. I don't know. Are you familiar with the Celsius scale? Because I don't know Fahrenheit.
No, not yet.
Okay.
It's something I have to start learning about, though. That's for sure. Celsius. We used to do Airbnb, and at one point, I think we had a few different times people from Germany visit. I don't know exactly where this couple was from, but they left a thank you note when they left. And they had mentioned that every American Airbnb that they've been to, there was at least one clock that was wrong. Is that anything? Is your clock right? Are all your clocks right?
I think, yes.
Is that like a
you mean like German have to have all
everything precise and everything like in line? Or is that a stereotype?
It depends on the type. It's a stereotype that sometimes gets validated. So
yeah,
my brother, for example, he changed his clock about a few days ago, because in Germany we have a time changing from winter to summertime.
Okay.
And this was in October, and he did it a few days ago. So
nice.
Not everybody.
Yeah, it's based on individuals. That makes sense. Yes. So something I'm curious about is you're studying physics. What sparked your interest in physics originally?
I think it was always a fascination for technology. So when I was little, I remember being about, 8, 9 years old or something. And every time we had a electrical device go broken, I would take it apart.
Okay.
Sometimes I could fix it, but not most of the times. And I wanted to know how it works. And then, to be honest, when I was finished in school, I didn't know what to do. Mm-hmm. Then I thought about that, and then I started studying electrical and information engineering.
Okay.
Or more precisely, electrical and information technology was it called.
Okay.
But then I switched to physics after one semester, because I was more curious about the deep underground over the principles that you learned. And I already had one physics class. The other ones were more like engineering, but I'm still interested in the application of the knowledge. So okay. In physics, if you get into physics after physics bachelor, then it's very abstract. Okay. So there are 4 specific types you can choose for the masters at my university. And the most common one is about nucleus, particle, and astrophysics. And it's either about the very small or the very vast, but it's not, you can't grasp it. So it's very abstract, and you're just designing some particle accelerators or detectors or something, and then you see the result on the screen. So it's not like what I think about as practical.
Okay, so you're more practical. You want to figure out how to put it into play
and work with something. So
okay,
that's why I really like the lab courses that I had and also having now. So I already wrote about the experiments.
Okay, so you're already doing experiments, and are you one of these things, nuclear, particle, or astrophysics?
No, I originally wanted to go to applied and engineering physics.
Okay,
but now I switched to biophysics.
Biophysics.
Yes.
Interesting.
Because I have a topic for my bachelor's thesis, which is in this direction. So I asked the professor what he thinks, and said biophysics would be the best choice for this. And he also said for the future, I think it would be very important. So it's already a rapidly growing market.
What? Yeah, elaborate on what biophysics is.
Okay, there I have to say one master's that I was thinking about to take was Matter to Life. It was called Matter to Life, okay. Which was also something I was curious about, because as I learned in school that basically everything is made out of atoms, then I thought, okay, I'm made out of atoms, yeah. And the stone is as well. Why am I living and the stone isn't? Or is it? Maybe.
Okay.
And that's I think what this master's is about. So when does matter become life? But as I said, I'm now doing at my bachelor's biophysics, and I'm actually not doing a physics master's. I'm going to switch. But biophysics it's about, I already did an experiment there at the Center for Protein Assembly. And it's about, the group, it was about cell biophysics. So it was about, I just want to explain it with an example. I think that's the easiest. It was about the molecular procedure that makes your muscle work. So okay. explaining biological structures and how they function with physics, and also a lot of chemistry and computer science, and also in this specific group with machine learning and artificial intelligence, and using this to make new concepts to create new medicines.
Interesting. What would be like the first thing I thought of was like prosthetics. Is that kind of in that realm or no?
Yeah, I actually saw something about this a few days ago, and I think it's more like classical mechanical engineering, but also there's the interface where you can use the signals from the human nerves to actuate the robotic extensions. But okay. I think that's more neurobiology than biophysics.
Okay. So then what would be an example of like medicine from it?
That's not actually the part that I would do. So
Okay.
I don't know yet. Maybe I
Okay.
get a little bit involved in it, but the thing that the group that I'm going to join or joined is doing is they take human cells from don't know the second one. Is it pancreas in English too?
Mm-hmm.
Yeah.
Yeah, the pancreas.
From pancreas. They take cells from breast and pancreas cancer, and then they put them in a dish and let them grow to little organoids, they're called. Okay. And then they analyze them with a microscope. And my part would be to predict how it would grow. And then you take your newly created medicine and treat the organoid in the dish with it. And then you compare it to what your prediction would be if you hadn't treated it with the drug.
Interesting. So you're kind of applying the, like, on an atomic level, what would happen to this matter?
I don't think we are going that deep on the on the cellular and molecular level.
Okay.
Because we're using optical microscopes, and getting pictures of atoms is pretty hard.
Okay.
So then you would have.
So atoms are the smallest. Molecules are bigger.
And no, you can go even smaller, but that's another story.
Wow. Dang.
But that's also one thing that fascinated me a lot when I first heard it. As I said, you can go smaller than atoms. Of how many things is everything around you and everything you've ever seen build up? How many different basic building stones are there? From what you can see, there are more, but from what you can see and
like, are we talking in my immediate space right now?
On the whole planet.
Yeah. It's a lot. Like a lot. So
no, not the numbers, not the number of how many, but how many different types, I meant.
Oh, okay.
How many different types of basic building blocks? What do you think?
Okay, it's either a small amount or a really large amount. I'm gonna say a small amount, like 5 different types.
Actually, it's only 3.
3? Okay. I was close. I was like,
yeah, it was close.
Okay.
And it was the right idea.
So everything in the world is made up of like 3 kinds of building blocks.
Yes. So the difference in everything you can see and you interact with comes from how it is built, not from what it is actually.
Not what it is, how it's built.
And one thing that's also pretty awesome, I think, is that if you go one level higher, then there's also 3, because 2 of them build another 2, and then the mass, most of the mass, so what you experience when you get on a scale, comes from energy. So you have protons and neutrons, and over 98% of the mass is energy, and the protons and neutrons are built up of up and down quarks, but they only made up 2% of the mass. The rest is binding energy.
So binding energy makes up
98% of the mass.
Binding energy. Let's back up for a second. How would you describe physics in simple terms? In simple terms.
Okay. I also thought about that, and what I sometimes learned at university was it's developing theories in order to make predictions about the future. So what's happening, what will happen. And a more poetic way to say would be try to understand the universe and everything inside of it.
Okay.
Which is not false.
Yeah.
And a more pragmatic way to think about it would be understand and predict interactions of particles and accumulations of particles.
So say that again.
From molecules up to an airplane.
Okay.
But I think this would be then more like engineering.
Okay.
But you can't do engineering without physics.
So physics can be applied to absolutely everything.
Yeah, there are some black spots, I would say, and one of the huge black spots is like dark energy or dark matter. I don't know if you ever heard about it.
I'm drinking dark matter coffee right now. I don't know if you can see that. What does that mean? Dark matter.
Yeah, the name is the program, as you would say it in German. So dark matter is called because it is dark, which means it doesn't interact with light, and that's why it's so pretty damn hard to detect it. Okay. And that's also why we haven't detected it yet directly. But there are few things in the universe out there about, for example, the radial velocity of galaxies, which if you calculate the mass of the galaxy, then calculate how fast it should spin, so that the gravity that pulls the planets and stars to the inside, and the force because of the spinning that pulls them to the outside cancels out, then you get that they're spinning too slow. So one explanation would be that there's another type of matter that we haven't seen yet, because there are only 4 basic forces, and 2 of them only play a role in the under the atomic scale. Okay. The other 2 are the electromagnetic force and gravity. So you can see the effect of gravity, but you can't detect it with electromagnetic forces. That would be light. So that's why it is called dark matter.
Wow. Okay. And
also kind of because I think because we don't know anything about it, really. Nobody knows what it could be. It's a huge mystery, and I'm sure there are a lot of wild theories about it, what it could be. And I also had an exercise about it, and there was it was about the rotation of the galaxies, and then calculating down how much matter there would have to be in order that it would fit the data. And this would mean that you have now 500 dark matter particles in your body, if this is the right theory.
How many?
500. Yes.
It doesn't seem like a lot, is it? I don't know.
It is not a lot. It is not a lot if you think about that in 1 cubic centimeter of air, for example, you have 10 to the power of 23 particles. So a 1 with 23 zeros.
Okay. Huh.
Then 500 is not many.
Yeah. Yeah. That's in like an average human, like a generally.
The particles in an average human, you mean totally?
You said 500, right?
Also, yeah.
Okay.
That's okay. Yeah. I don't know exactly what numbers we used, but because you have to calculate it with the volume, and I don't know exactly how much volume we took. So maybe for
okay. Something I hear or read is that like the big breakthrough of the 20th century was physics, and like the 21st century is looking like biology. Can you kind of
can you say that again? The connection
was
lost for a second there.
Something I hear in conversations or something that I read is that the 20th century, the big breakthrough was physics. And then the 21st century, it's biology now. Can you kind of describe what went on studying physics in the 20th century that it became so profound?
A lot, really a lot. Most of the things, yeah. Sounds funny, but it's I'm not searching for the words. I'm not making it seem more important than it was, because there were whole new fields evolving and created in the 20th century. So as I already said, there are 4 basic forces, and it's kind of always has been a huge goal to connect them all to one theory. So that has worked for 3 of them in the 20th century. So you have the weak and strong nuclear force, and the electromagnetic force, as I already said. And then Richard Feynman came along and invented the Feynman diagrams, where you can put a particle interaction that would have a formula to describe it, fill in a whole page in one simple diagram. And this makes it a lot easier. And then also the quantum field theory evolved, which means that the particles that you think there are not actually there, but there are excitations in a field. So for every particle, and there are basic particles in the standard model are, I think, let me think for a second. You have 6 quarks, 6 leptons, and then I think 9 bosons, and then the Higgs boson. So about 20 or 30 basic particles, and the interaction between them you can describe with the Feynman diagrams. But then it was a theory from the 20th century, which was also huge. Where do they get their mass from? Because not all of the mass is, as I said, binding mass. And there was this theory in the 60s or 70s about the Higgs boson, which was then discovered in 2015.
This is the, what'd you say? The
Higgs boson.
Say that again. Did you say the can you repeat it again?
Higgs boson. Higgs boson. Named after Peter Higgs. Higgs.
Yeah, the Higgs. Okay.
The Higgs, yes.
So what did that say? That was about the mass?
Yeah. There's the Higgs mechanism that gives every other particle the mass, acting with this Higgs boson. And in the lecture, my professor had a analogy for this. It's like if you're a waiter at a party, and there are no people, then you can walk through the hall, no problem. But if you're a waiter with a lot of drinks, and then there's a party with a lot of people, then you get stuck here, there, and everywhere.
Yeah.
And that's kind of what the Higgs field is. So there's a field all around us, which has a value at every point in space. And because every particle interacts with the field, they get mass.
Okay.
And then the other thing that I wanted to talk about is Einstein. And then the mass curves the space-time. So then time and space are no longer constant, as you may have heard sometime. Have you heard about the theory of relativity?
So is that E equals mc squared?
That's the general theory of relativity. That's that matter is equal to energy.
Okay. Okay.
That was also Einstein. And another.
So these are two separate things.
Yes.
Okay. Go back to the first one.
Okay, but one thing I just want to mention and can elaborate later is quantum mechanics was invented in the 20th century, which is also really important. But yes, basically, if you increase your velocity through space, then your velocity through time decreases. So in one sentence, moving clocks tick slower.
Because they have to actually physically move, and it takes up space in a way. It takes more time because it's physical, rather than if it was clear, then it'd
be... The connection was lost for a second again.
Oh, sorry.
The connection was lost again, sorry.
So the clock moves slower in physical because there's more particles in the way, rather than time, there's nothing in the way. It just happens, right? Or
it's not that the clock, you should not think about the clock anything moving or something.
Okay.
It's if I let me make a thought experiment. If I would travel with a huge speed, there's a speed limit. You can't go higher than this speed, which is the speed of light. But if I would travel close to the speed of light for 1 year, then maybe for you on the Earth, 10 years had passed. And for me, only 1 year. The problem with coming back and then being in the future is a little bit more complicated. But if you can solve this, then you could come back to the Earth and maybe 500 years had passed. And for you only, depends on how fast you've been. Maybe minutes or days, and on the Earth, centuries or millennia. You just have to get fast enough.
Okay. Would then your particles all still be the exact same?
It would be for me like 10 minutes had passed. But the thing about this is you can't actually increase the time you live by this. Because for you, it's 10 minutes. And you can do this over and over again. And on the Earth, the time would pass very fast. But that doesn't change how you perceive the time for you. So you would still like live 80, 90 years. But you can more or less jump to the future. And I also, a lot of times when I see something about this, is time travel possible, then one of the best answers I think is yes, and you're doing it right now, because we are all the time traveling into the future. Wow. It depends just how fast you do this. And this means the other perspective, if my clock is ticking slower, which happens when I'm moving faster, then your clock would be ticking faster. That's why you could, if you could make it technically possible, but as I said, coming back and then returning is a little bit more complicated because this only works for constant speed. So it's not that sure if a round trip back to Earth would work. But there's another way how you could do this. Okay. You just have to go, maybe you saw the film Interstellar?
I have not,
or
but
heard about it.
People have told me about it.
Yeah, and it's quite accurate. If you go near to a black hole, then the same thing happens. Your time goes slower, and then if you come back 55 years, 52, I think it is in the movie, could have passed in for you minutes.
Wow. So do you see so what is the name of this theory called?
Special theory of relativity. And by the way, for a lot of things in physics, you may ask, how do I need this? Why do I need to know this? And for this specific theory, GPS only works with this theory, because the GPS satellites in orbit are calculating your position depending on 4 satellites. Okay. And then they calculate the distance from each satellite to you by measuring the time the signal takes to you and back to the satellite. And therefore, they need really accurate clocks, more accurate than a nanosecond. So they are really fast, spinning around the Earth, and have a really accurate clock. And if they wouldn't calculate for the time their clocks are spinning slower, then your GPS would be false, I think, about 3 meters every hour, 3 meters more.
Wow.
So in a day, more than 60 meters, 60, 70 meters. Your GPS would go wrong 60 meters every day. And counting if you wouldn't consider the slower clocks for the satellites in the calculation.
Okay. Wow. What other things can you use it for?
For example, discovering new physics. It's always used, or more or less, it's just a byproduct. The math, the basic math with this theory is pretty simple, and you just have to calculate one factor, and that's the factor how much your time is stretching, or also your distance is squishing, which also happens, by the way. And for the small particles that are getting accelerated in Switzerland, in France at CERN, you may heard about it. They are going so fast that they experience time 40 times slower than we are. So there are some particles that live only a very short amount of time, but because we are experiencing the time faster than they do, we think they're living longer, about 40 times than they actually do, because they're spinning so fast.
Wow.
And I think that this is also the high speeds that you can observe anywhere, except of light particles, because they're traveling at the speed of light, and you can't reach the speed of light, because as you move faster, your mass is also increasing, which means you need to have more energy to go even faster, and then your mass is again increasing, and then you have to have an infinite amount of energy to actually reach the speed of light, which is obviously impossible. But that's not a really practical application for the average person, I think.
Do you think we'll get there?
You mean
like as a human species in the future?
Going so fast to experience the effects for time travel.
Yeah.
I heard the kind of longest. The word longest kind of loses its meaning if you talk about time traveling. But the longest time travel any human ever did was a Russian astronaut who was more than a year in space, and he did about 0.02 seconds jump into the future, which is not so much.
No.
But yeah, if you drive with your car, you only have about 0.0000000000001 seconds. So it's a different story. But I think yes, maybe we will get there. I'm pretty sure we will get there. And there are a lot of ideas to accelerate that fast.
Okay.
But all of them are a hard engineering problem. And
I can imagine.
I think to time travel, because as I said, time traveling we're doing all the time. If I wave my hand, it's traveling through time slower than I am. So there's no discrete difference where you can say I'm time traveling and I'm not. So it's a continuum. But like years or days, probably this century, maybe. But maybe the idea with going to a huge mass and therefore going faster through time would be the more practical way, because then you don't have to accelerate that fast. But the problem is the next black hole is really far away, so you then again have to go really far and therefore get really fast.
Yeah. Can you break down what quantum mechanics is?
Okay.
He's like, here we go.
I heard. I don't know the name who it was again. He was asked kind of the same question, and it was, can you summarize quantum mechanics in 1 minute? And there's I would steal his idea, and okay, he kind of stole it too, because it was originally from Richard Feynman. As he was a student, there's a famous experiment in quantum mechanics, and he asked his professor what would happen if you augment the experiment, and that would mean that you think about a particle that goes from 1 to B, and then you think about every possible way it could go, and then you sum up every possible way multiplied by its probability that it would take this way, and then you get a distribution, and which is in time and space. So the particle is no longer a physical particle, but it's a distribution function which evolves through space and time. And then when you measure it somewhere, you measure it with according to the probability distribution of that particle.
Okay.
And there are a lot of really weird things going on. One of the weirdest I heard a few days ago is called the quantum eraser, which means if you have a specific experiment, then you have a screen where you detect something, and then you have another screen where you detect something, but you detect on the other screen afterwards than on the first screen. But what you detect on the second screen influences what you detect on the first screen in the past. So you change the past by detecting or not detecting.
Wow, that's wild. So quantum.
Quantum, the where it comes from. By the way, Albert Einstein had his Nobel Prize for a quantum experiment, a quantum particle experiment, not for his theory of relativity.
Okay.
Because by that time, most of the physicists about him thought he was crazy, because everybody thought about, you have space, you have time, and they just go on and stay constant. And then he says, okay, no, we have just one constant, and that is the speed of light. And that then he concluded that space and time can't be constant. So time can stretch and squish, and space too. But that's kind of a wild idea. But now it's most of the one of the best proven theories in the world, as quantum mechanics is too. And the Nobel Prize he got for the explanation of the photoelectric effect, which means you have a light source and point it to a metal, and then you can extract electrons, and that only happens if the quanta of light have enough energy by their own, and that implicates that light is quantized. That's why it's called quantum theory or quantum mechanics, because everything is quantized, which means it comes in discrete packages. So you kind of can split everything, but then you have something that you can't split any further. And that's the same with energy, and maybe also time and space, which means kind of there's not a infinite resolution of reality. So like your screen, reality is pixelated, but on a very tiny scale.
Okay.
And that's why it's called quantum mechanics, because you have a quantum of light, you have a quantum of energy, you have a quantum of angular momentum. And by the way, maybe you heard the phrase quantum jump before?
I think so, yeah.
Or quantum leap.
Quantum leap, yeah.
Quantum leap. As we had it in the lecture, my professor said, "You think that's kind of funny that it's called quantum leap because it's the smallest possible step you can take."
Wow. It is funny.
But I think it is called quantum leap when you say it, you mean a huge jump, because for some experiments like the photoelectric effect, you can have light with specific wavelength and frequency and energy, and then each quanta of light gives the material a little bit of energy, but it changes nothing. And then if you get the frequency higher, then suddenly the quantum jump happens. That's why I think it's called quantum leap, because you put in a lot of work and nothing happens and nothing happens, and then suddenly you have a quantum jump. Yes.
Wow. Cool.
But again, it's the smallest possible jump. So
nice. Let's see. How can we apply concepts from physics and related sciences to solve problems of the 21st century?
Okay. One of the people at my university in the first semester told us that we're teaching you how to think. And now I get what he means. Because you're really doing problems and doing different theories, different parts of physics, but the basic thing that you're learning is how to approach a problem. And then one of the concepts in physics, or for most in experimental physics, is to get the human out of the loop, because you can't trust your own sensors.
Okay.
So you always try to make a really objective measurement device, and that theme goes through whole physics. So you have the scientific method, which is based on keystone concepts, so that it gives you kind of a cooking recipe for finding new truths about reality.
Yeah.
And one of the most important things always in experimental physics is falsifiability. And I had one evening where we had a meeting that was called Meet Your Prof, where we get together with our professors for a beer and talk about what they're doing at the work.
Cool.
And then one of the professors, math professor originally, math professor, and then switched to physical math. And another one, which was my my lecturer for math for experimental physics, had an argument about string theory, because he did some string theory, and then Professor Bartel, she said, yeah, but it's a theory where you can kind of say anything, but a problem with it is you can't falsify it. You can't falsify it.
Okay.
Because in order to do it, because the things, the strings would be so tiny, you would need so much energy that you can't observe them. And that's why it's kind of getting a bad rep in the physics community, because you can say anything, but you can't falsify it. And that's one of the most basic constants, that you have a theory that you can falsify. And I think for this concept is really important, that you can apply for a lot of things apart from physics. And what I really like about physics and other related fields is the kind of not if in an argument, in a discussion, it's not I against you, then it's more like you and me together discover the truth. And
I like that.
I think in a lot of fields, it's or in a lot of public arguments or discussions, it's the first one. So I think the last one is better, and I always see this with my professors. If I say that there's something wrong with something, or bring another idea up, then they always take the time and think about it, and are not even single for a split second that they want to make the point that they are right and I'm not. Because they're as curious as I am about discovering the reality.
So they're not eager to dismiss you because they want to find out if it's true or not, is what you're saying?
The first part was lost in the connection. Sorry.
So what you're saying is that it's like a community of curious people that are open to ideas, and the goal is to like find truth ultimately.
Yes. Okay. Yes. And they're always thankful about other ideas. I remember one of my favorite professors was from Canada, and he did the same topic, the same lecture, but in it as I already had in this semester, but first of all in English, and then with a whole other concept of teaching, I would say. And we were that time about 650 people in the year, and only about, I think, 20 or 30 got into his lecture because it wasn't necessary, because he already had the topic in another one. And it was more like face to face with him, and almost all the time we stayed after the lecture with him and discussed other problems.
Wow.
Sometimes for 2 hours or more, and he was really passionate about what he did, and you could see how we influenced also his way of thinking, and it was kind of a magical experience where everybody learned from each other at the same time.
Wow, that's really cool.
And most of the time when I think back to school, it wasn't that way, because most of the teachers I had, I think they just wanted to be right and think they know better than us.
Yeah.
And I've never had this experience in university at all.
Wow.
And I think that's a huge part of the scientific community all around the world.
So what possibilities through science excite you most personally?
Okay. one of the things that I definitely want to go into, and is also one of the things that physics concepts can be applied to solve problems of the 21st century, is climate change. So in a lot of different ways, or also now it's COVID, with the first part measuring and creating knowledge, and then innovating on the based on that knowledge to find solutions. For example, at my university, there are a few projects for or against climate change, I would rather have to say, like electric vehicles, or now the carbon removal price or competition. It's a X prize competition. It's, I don't know really what it is, but it's kind of a competition where somebody says, I take a huge amount of money or something as a prize, and then you have to get into a competition. And the Musk Foundation from Elon Musk made a prize for $100 million until 2025 for the best carbon removal system. So getting the carbon out of the air. Then there's the Hyperloop initiative for long distance fast transportation. These are some of them. And another really really exciting topic, of course, is space exploration.
Okay.
Which also, of course, has to go with a not environmental damaging technology. So there are also a lot of concepts, like one of the funnier ones I heard about lastly was kind of I don't know the exact English words. If you have a powder tree, so and then you take a stone and a rubber and you put it back and let it go. Slingshot. Kind of a slingshot for rockets.
Wow.
So they have a huge building where they rotate a rocket until it's 6 times faster, or even faster than sound, and then just let it go. And and hope it's fast enough to stay in orbit. So you have less fuel burning, so it's better for the environment. But I doubt that it will work soon.
Yeah,
because there are a lot of problems.
Well, yeah. Who would you say, or what are like 3 influences that have shaped your outlook on life?
I mean, people. No.
Let's go people.
Okay. I first thought about, actually, which I was surprised by myself. Anne Frank. Have you ever heard that name? Anne Frank, I think you would.
Anne Frank?
Yes.
Anne Frank, really?
Have you heard about her?
Oh, yeah. Yeah, we've all read her book, her diary.
Yeah, I was actually at the garbage dump in my village, and there we have a place where you can put things that are good for other people to grab.
Okay.
And there, I don't know, 6 years ago or something, I grabbed her book there, and this was actually the first one I thought about because of the way how hopeful and kind of not disturbed she went through her day. Yeah. In that time, in that place, in that situation. So she was a little girl getting up, doing her school stuff, learning French. And when I think about day-to-day problems from other people, then I see how they complain about everything.
Yeah.
Sometimes I think about people like Anne Frank. I think they were in this situation and they weren't complaining at all and loving what they're doing, loving to have the ability to learn, to still hang out with some people. and I think that's very inspiring. And she was pretty mature, I think, for her age, and really is inspiring for the motivation to persevere in this extreme and long-lasting situations. And she didn't know how long it would last.
Yeah. Wow.
I think that's really inspiring.
That's a great one. Do you have any more that you're inspired by?
That's the second one is someone I really enjoyed listening to, a podcast, actually. Lex Friedman. I don't know if you ever heard about him.
Oh, Lex Friedman. Yeah, I like Lex.
I think it's pretty awesome, and I'm on my way to catch up because I started at the first episode.
Okay.
When there were about 130.
Okay.
And now I'm, I think, about 40 episodes still behind, but I catched up. So I catched up 90 episodes. But man, he's really putting out 2 to 5 hours every week, sometimes 2 days in a row, or nearly 2 days. It's I can't think about how he did this, but yes, he has great guests. I think if you heard him, then you know. And it's a lot of the time it's about technology and physics or computer science. So that's what I like. But also the philosophy part. It's I
really enjoy that a lot. It's cool he's like so intelligent and has this like beautiful perspective about the world and this like philosophy that he's trying to explore.
Yes, that's really great, because the connection also with him about technology and philosophy I really like. And as I someday I tried to figure out where physics came from, and actually it was created from nature philosophy, and then emerged from the field of philosophy, physics. So we sometimes also had this in lectures where they say that the idea of atoms, for example, is really old. It's more than 2,000 years old from the old Greek philosophers. They thought, okay, if you always split something, then you have to get down to the smallest splittable thing, which they call the atom, from atomos, which is Greek for not splittable.
Okay.
But as we now know, it is. But the name stuck. And also the name electron, it was discovered later, but it's also from Greek. I think I don't know the exact story about this, but a lot of the ideas or the basic building blocks of physics are from old philosophers.
Wow. And then who would be a third person?
Not one, but many.
Okay.
And maybe right now the most important, because I'm not sure if we would have this conversation right now if it wasn't for them. It's a YouTube channel from the States, from LA, called Yes Theory. Have you heard about it by any chance?
I have not.
It's awesome. You have to watch it.
This is the first time I'm hearing about this.
It's awesome. It's, as I said, it's called Yes Theory, and again, they're doing what the name implies. It's about the idea to go out of your comfort zone and say yes to more stuff, and they are doing a lot of things to show this for themselves and to other people. So actually, most of the time at the beginning, I've watched them for about, I don't know, 3-4 years or something.
Oh wow!
They did a lot of stuff with strangers, and also still doing, and traveling around the world and meeting strangers, or putting themselves in uncomfortable situations. For example, like surviving 24 hours in Istanbul without speaking the language or having any money or phone or something. Okay. And it always ends up in experiments with strangers. which are friends you haven't met yet, as you may know.
Yeah.
And it's a great way of living this idea. I think how I see it with them, and that's one of the reasons I say yes to your invitation.
Yeah, that's awesome
for the podcast.
Well, I have one last question for you. It's been a great conversation. What's something you're curious about recently?
Okay. Could it be only one?
It's up to you. Your discretion.
Okay. It's not recently, but it's been longer now. It was September 2021. No, September 2020. It actually was where I had it was called Introduction to Scientific Programming at university, and that reignited my interest for coding in general.
Okay.
And then I because I the first time I was at in the 6th grade, I think you would call it extracurricular activities or something.
Yeah.
Something. Yes. We had a kind of a MINT program, STEM. It would be for you, STEM.
Okay.
Science, technology, don't know.
Engineering, mathematics, probably something like that.
And engineering. Yeah, I think so.
I'm just guessing. Those are.
But I think you're right.
STEM. Yeah, right. STEM. Yeah.
Yeah, it's in Germany. It's MINT. It's mathematics, informatics, technology, and natural science.
Yeah.
Yes, but in the 6th grade, I was in that program, and we went to university and started programming ants. So it was a game where you programmed a simulation of ants.
Okay.
And yes, then I had computer science up to my Abitur, so graduation of school. But in retrospect, I think the teaching style was pretty bad.
Okay.
There was one good teacher in one year, but the other ones, most of the time, and a few times, it was actually most of the time. Some students knew more than the teacher, and some of the time it became pretty obvious.
Oh yeah.
For example, if they ask for help. But now at university, I discovered my interest and started teaching myself for now 1.5 years, and now having done a few little projects, and now I will do my bachelor thesis also in that area, as I told you, which the title or the title it may change would be AI and machine learning tools to analyze organogenesis, which is the building of organs, so organogenesis. And then I'm most certainly will do a master's in computer science called Robotics, Cognition and Intelligence, which is also focused on artificial intelligence. And that's I recently, firstly 2020, but I would say the last few weeks and months more intense doing this. And now starting at the group at the Center of Protein Assembly, but my professor is still in the US, so he's nearer to you than to me. I don't know. Is there some restriction for traveling or something? Because originally he wanted to be here by February, and we would have a meeting, but now he's still in Boston.
I'm not sure. Yeah.
And the second one I would say is languages. One of them in particular in the last few weeks, but it's hard to find the time.
What do you mean by languages? Like learning?
Learning languages. Actually, I had to repeat a year in school for the language. But it's different if you want to do it than if you have to do it.
Yeah.
And now I want to do it. And it's the language that it's actually spoken because in school I had Latin.
Okay.
Now I'm learning French and Japanese, but it's Japanese in particular is pretty hard.
Wow.
Yeah, that's what I discovered recently, I would say.
How many languages do you know right now?
English, of course, then German, and in the order I would say German, of course, the best, then English, then French, and then Japanese. But
Wow.
French. I was in France a lot of times.
Okay.
And some of the people there told me my French is better than their English, but for some of them that's not really hard because it's that way. They say it to me also, but I take it as a huge compliment because I don't think my French is that good, and Japanese is I'm just starting. It's so hard.
Yeah.
I know a few words, a few phrases, but that's all.
Okay.
So maybe English and German.
Nice.
How about you?
Just English right now, but I need to get way better at my Spanish.
Yeah, that's what I thought. Not that you have to get better, but that Spanish would be the second choice because I think in North America, specifically in North America, I think most of the other languages is it's Spanish.
Mm-hmm.
Most of the people that doesn't speak English as their main language speak Spanish, right?
If you can speak Spanish, you can probably get by anywhere in the Western Hemisphere.
I don't think so.
You don't think so?
No, I don't know how it is in the US, but I know not so many people who can speak Spanish here, and haven't met either in Europe. So,
well, not Europe. I'm talking like North and South America.
Okay, because if you say Western, I would say I thought you would include Europe also.
Okay,
America, yes.
Yeah,
I think so.
So I'm working at that. What's your process? I feel like how do you learn it? Do you do it through like apps? Do you read the books?
Actually, good to bring up maybe. Last time I was in France, I bought the famous French philosophers in French.
Okay.
But it's a double challenge because I think even in German or English it would be hard to read. Like
that's pretty substantial.
Descartes, Sartre, and Voltaire.
Okay.
Yeah, but I also bought a science fiction book, which I take a look into, and then I thought, okay, I understand something. Maybe I should start with this one. But haven't started yet. One time I tried, but it's still hard. I sometimes switched Netflix to French.
Okay.
To get familiar with the language, but I think the best way is to learn in the country.
Yeah.
I learn with an app every day. Okay. But I think you learn the words, you learn the phrases, but you don't really learn the language and how to use it. And that's why for Japanese, for example, I want to start a book where I write the signs, the Japanese signs, and learn them there, learning by doing, and then maybe also trying to hear it more. I also search for podcasts where you can learn it, because I think hearing is very essential. And then maybe I'm planning on doing a half a year abroad at my master's, maybe to Japan.
Ooh,
or to France, maybe. We'll see. But as I said, I learned more in France than at home. So
yeah,
in 2 weeks than in 2 years at home. You really have to, and it's for me, it's really easy to get in contact to other people, especially there where I'm going basically every year with my family. It's a little village at the Atlantic, and they also, by the way, have their own Statue of Liberty.
Oh, nice.
Because the Statue of Liberty from New York came from there.
Okay.
It was
so like sailed out of there.
Yeah, it was. As you may know, it was a gift from France to the US, and that was the last time. So this village to saw Europe.
Oh, that's cool.
Before it left to the US. So there have a little Statue of Liberty with French and US flags around it.
Oh, that's awesome.
And yeah, and meeting there the people, and at the first time I didn't found that many people to speak English with, and then I just translated all the time with my phone with Google Translate, and it worked. And then I found a barkeeper, which I meet now every year there when I am there.
Oh, cool.
And he's pretty good at English, so that's easier. But I tried to learn French and try to speak a little bit French with him. But yeah, that would be my progress. Going there and learning there.
Cool. Well, thanks for sharing that. And thanks for the conversation. This has been great.
You're welcome.